This is CPE 133. We're in Chapter 11, the free-range Verilog Foundation modeling text. We're going to talk about D flip-flops and latches, and namely how Verilog chooses to model those. So it's not particularly intuitive, but it's very doable. There it is, the disclaimer. To learn Verilog, you need to actually code some circuits and model some digital circuits. You're not going to learn it by watching a boring video or reading about it. It's going to help, of course, but you actually need just to break down and do it. So I encourage you to give that a shot. So we're moving into sequential circuits, and sequential circuits, of course, is a circuit with memory. And the two most basic elements we have out there as far as memory go in digital design land are latches and flip-flops. Now, latches and flip-flops are simply 1-bit storage elements, but they're a little bit different. So there's a couple different types of flip-flops out there. We only deal with D flip-flops. The other ones were for older people, if I'm allowed to say that. But essentially, we have been talking about latches for a while. We've been doing what we can to avoid generating latches. We'll do an example in here where we actually generate a latch on purpose, but that's something we just don't use that often. Most of digital design is involved with synchronous design, which means D flip-flop. So the difference between latch and flip-flop is D flip-flop is synchronous, meaning that the flip-flop changes in the output of the flip-flop are generally synchronized with the clock edge. And so this happens to be a rising edge clock, a rising edge triggered clock. I don't ever put this in here unless I really have to, but that's what's understood to be there. So there's also a falling edge trigger. If that had a little ball in front of it, that would be a falling edge trigger. But the notion of rising edge trigger essentially means that of a clock signal here, changes happen on these rising edges only, and that's the only time the flip-flop can change. Now the latch here, generally speaking, it's considered a level sensitive device because changes aren't synchronized with anything. They're asynchronous. Asynchronous level sensitive. These are synchronous and they're edge sensitive. So let's delve deeper into that. So there's two ways to generate a sequential circuit using Verilog. Number one is you incompletely specify the outputs in a procedural block. That means you don't provide an output for every possible input combination. Now the ways, essentially the ways to avoid that is to include a catch-all, but if you don't include a catch-all there, it essentially stands the possibility that you didn't define every input. So once again, incompletely specify the outputs for a given always block, you can end up with a sequential circuit, which we generally refer to as a latch. The other way is we're going to use these two functions here, and once I use these two functions, these are, as you can see, they're kind of they're inherently edge sensitive. I mean, to look at it, the functions have edge in them. And essentially, it forces the synthesizer to generate registers, whether it be a 1-bit register like a flip-flop or any type of register. They're just all essentially synchronous circuits that store values. That's what these two functions are going to do. So once again, once I use these in my code, that code will be a sequential circuit. It's just a rule in Verilog you get used to. So the first example here is we're going to model a NOR latch, and once again we just don't use that too often in digital design land. But here it is. You got what do you have here? A circuit with 3 inputs. SR are the inputs and 1 output. So it's 2 inputs and 1 output. And essentially, if the reset is on and the set is off, it's going to reset, and you can see that right here. Otherwise, if the set is on and the reset is off, it's going to set, and you can see that right here. So the thing to notice about this one is it is a sequential circuit, so we are using non-blocking statements in here. Additionally, we are assigning Q as part of the always block, so we have to declare it as a reg here. The circuit itself is sensitive to S and R, which notice we did not use a pos edge or neg edge in there, so this is inherently a level sensitive 1-bit storage element that we know and love as a latch. The fact that it's a NOR latch indicates essentially that whether the S and R are use positive or negative logic. For NOR latch, of course, uses positive logic. There's also a NAND latch, which would be using negative logic, and essentially that would just matter of swapping 0 with 1s in this circuit. Anyway, there's a latch. We don't use it that much, but somewhat instructive anyway. So that's next thing we're going to do is move up to D flip-flop. And let's look at this thing. And this is, simple D flip-flop. It's a synchronous circuit. It's a 1-bit storage element, and here's the model for it. So it is, being that it is synchronous, we have used this pos edge function. Once I use that pos edge function, it guarantees that anything I assign in that circuit is going to be a register. We've only assigned one thing in this circuit, which is Q. Because it is a sequential circuit, we are using non-blocking assignments here, and Q is declared as a register because it's assigned within an always block, and I just don't know what else to say about this circuit. Generally speaking, not too useful of a circuit. It needs some type of load control, which we'll get into in the next chapter when we talk about registers. So we're going to modify this D flip-flop to have a asynchronous clear signal, and I know that it's actually active low too because of that bubble here, but that means the clear signal, when it's asserted, it doesn't need to wait for this clock edge, and that's where the asynchronicity comes on this one. So let's take a look at this solution. And so this one, it's looking at two items here. Of course, it's kind of looking at the pos edge, but it's also looking at it's looking at the pos edge of the clock signal, but it's looking at the neg edge of the clear signal. So a couple things to notice here. N clear kind of is a shorthand notation to indicate that it's active low, and you can see this. If one of these signals here kicks off this always block, a couple things are going to happen. So if it was truly a neg edge that did it, and that's a falling edge like this, then the signal is going to be 0 and the flip-flop is going to clear. So if N clear is a 1, that means it wasn't the neg edge that set this flip-flop off, it was actually the pos edge. And under those conditions, it's going to jump to this else and actually just put the D flip-flop output, the D input onto the flip-flop output. Okay, so once again, this is kind of the way to make this asynchronous. It's actually, if there's a negative edge, this is going to happen. Negative edge on the N clear signal, this is going to happen, which is clears the flip-flop. Otherwise, it must have been a positive edge that kicked this thing off, and the else is going to happen. So this looks very familiar. It looks like there's like an if and an else statement, and we know that an else is a catch-all, but in this case it doesn't matter. Anytime you use one of these functions, it overrides this catch-all here, and it's still going to be a sequential circuit. So the next thing we want to do is a same circuit. We want to make it synchronous, and the whole idea here is to get rid of that neg edge in here regarding the N clear signal. So once again, only thing that's going to kick this always block off is a rising clock edge. When there's a rising clock edge, the first thing it's going to do is look at the clear. If the clear is 0, it is going to clear the flip-flop and then exit the always block. Otherwise, if the N clear is 1, it's not going to do this. It's actually going to do the loading part of the always block. So once again, it's either going to clear or load on the clock signal. So these, this is pretty important information. It's actually pretty useful, and you can see these things together with the difference between the asynchronous and the synchronous clear. Just has the only difference is this little signal right here. And notice that I can use the pos-ev and neg edge in the same sensitivity list, but I can't use the pos edge and a neg edge on the same signal, which is, people eventually try to do something like that, and it just doesn't fly. So next, we're going to continue this later, and we're going to talk about blocking and non-blocking assignments, and that will be the second part of this lecture, or it'll be the next part, and we won't say second part.